Welcome to Marikamba PU College, Sirsi, Department of Physics.
In the case of a parallel plate capacitor, if the distance between the two plates is d and area of cross section of each plate is a, then the capacitance we have already studied is given by C naught is equal to epsilon naught a by d. Okay. Now if I place a dielectric medium here, if I place a dielectric medium which covers the entire space between the two plates, then the capacitance value becomes C is equal to K epsilon naught A divided by D. So therefore capacitance C is equal to, so K into C naught. Therefore dielectric constant is defined as, it can be defined as the ratio of capacitance of a parallel plate capacitor with dielectric to the capacitance with air as the medium. Now instead of placing the dielectric in the entire space, if the dielectric is placed as shown here, only a part of it, that means now I am writing the dielectric for a particular region and the other two regions becoming air medium. Now if T is the thickness of the dielectric and the distance between the two plates is D, then what will be the formula for the capacitance? Now look here, up to the thickness T, the dielectric is present, and for a distance of D minus T, air is present. Now here and here is, it is air or vacuum, air ide, illi matra dielectric idane. So dielectric constant K ಅಂತಂದ್ರೆ ನಾವು ತಗೊಂಡ್ರೆ air case ಅಲ್ಲಿ K is equal to 1 ಆಗ್ತದೆ. Then the expression for the capacitance in this situation, it is C is equal to epsilon naught A divided by, for air medium it is D minus T plus, for the dielectric medium it is T divided by K. Now that formula we are using while solving some competitive problems. Based on the shape of the capacitor, we are having different types of capacitor. Now here the plates are parallel, therefore it is called as a parallel plate capacitor. If the plates are cylindrical, then that type of capacitor is called as a cylindrical capacitor. If the plates are spherical in nature, then that type of capacitors are called spherical capacitors. Now we study combination of capacitors. Two or more capacitors are interconnected and that leads to combination of capacitors. Now capacitors are connected in two ways. First one is series combination and second one is parallel combination. Now first one is series combination. Okay, those are the two types of combinations, that is series combination and the parallel combination. Now two capacitors are said to be connected in series if they are connected end to end. One end of the capacitor anna innond end of the capacitor ge connect madidre, end to end connection madidre, now that type of connection of capacitors is called as a series combination anta kariteve. Now in the series combination, the charge on each capacitor is same. Series combination ಮಾಡಿದಾಗ ಪ್ರತಿಯೊಂದು ಕೆಪಾಸಿಟರ್ ಅಲ್ಲಿ ಚಾರ್ಜ್ ಅಕ್ಯುಮುಲೇಟೆಡ್ ಆಗಿದ್ದು ಸೇಮ್ ಇರ್ತದೆ. The voltage or the potential difference applied is equal to sum of the potential difference across each capacitor. ಚಾರ್ಜ್ ಸೇಮ್ ಇರ್ತದೆ, ವೋಲ್ಟೇಜು ಅಥವಾ ಪೊಟೆನ್ಷಿಯಲ್ ಡಿಫರೆನ್ಸ್ ನೀವೇನು ಅಪ್ಲೈ ಮಾಡಿರ್ತೀರೋ ಕಾಂಬಿನೇಷನ್ ಅಲ್ಲಿ ಅದು ಏನಕ್ಕೆ ಈಕ್ವಲ್ ಆಗಿರ್ತದೆ ಅಂದ್ರೆ ವೋಲ್ಟೇಜ್ ಅಕ್ರಾಸ್ ದಿ ಫಸ್ಟ್ ಕೆಪಾಸಿಟರ್ ಅಂಡ್ ವೋಲ್ಟೇಜ್ ಅಕ್ರಾಸ್ ದಿ ಸೆಕೆಂಡ್ ಕೆಪಾಸಿಟರ್. ಇಫ್ ದಟ್ ಈಸ್ ದ ಕೇಸ್, then two capacitors are said to be in series. Two capacitors are said to be in series if they are connected end to end such that charge on each capacitor is the same and the applied potential difference or voltage is equal to sum of the potential difference across the individual capacitors. Now we are going to obtain the expression for equivalent or effective capacitance when two capacitors are connected in series combination. Now, two capacitors of capacitances C1 and C2, they are connected end to end, that is in series combination. And an external battery or power supply of potential difference V is applied to the combination. Now, in the series combination, charge is same. Therefore, Q on both the capacitors is same. But what is the applied potential V? It divides into V1 across the first capacitor C1 and V2 across the second capacitor C2. Now therefore, by the definition of capacitance, what is C1 is given by the formula, it is charge divided by voltage V1. Now from this expression we can get, so what is V1? Voltage across the first capacitor. It is equal to, so simply Q divided by C1. Similarly, for the second capacitor, the capacitance C2 is given by, it is Q divided by V2. Now look here, voltage is divided but charge is same. Therefore, for the two cases we are taking Q as common, that is charge. Therefore, from this term, what is the voltage across the second capacitor? It is V2 is equal to Q divided by C2. That is the voltage across the first capacitor and voltage across the capacitor. We know that in series combination, the applied voltage is equal to sum of the two voltages, that is voltage across the first capacitor and voltage across the second capacitor. So therefore, substituting the values we will get, so V1 is Q divided by C1 plus Q divided by C2. Okay. Now here Q is common. I will take the Q common out. What I will get? Now V is equal to Q into 1 upon C1 plus 1 upon C2 I am getting. Okay. Now cross multiplying the charge Q, I will get, now V by Q is equal to 1 upon C1 plus 1 upon C2. Let me call this equation as 1. Adana equation 1 antandeli navu adana kariyuva. So next step is very important. That is, the combination is replaced by a single capacitor which produces the same effect as produced by the combination, and hence it is called as equivalent or effective capacitance antandeli adana karitivi. Now from this diagram I will write what is CS. Now CS is equal to effective capacitance is equal to, the charge should be the same. So ಇಲ್ಲಿ ಎಷ್ಟು ಚಾರ್ಜ್ ಇತ್ತು ಸಿಸ್ಟಮ್ ಅಲ್ಲಿ, ಅಲ್ಲೂ ಸಹ ಅಷ್ಟೇ ಚಾರ್ಜಸ್ ಇರಬೇಕು, ಡಿವೈಡೆಡ್ ಬೈ ದ ಅಪ್ಲೈಡ್ ವೋಲ್ಟೇಜ್. But here I am having V by Q. Now here it is Q by V. Therefore V by Q becomes, what we will get, 1 by CS. Now CS is called as effective or equivalent capacitance. Now substituting that value in the equation 1, I will get, therefore 1 by CS is equal to 1 by C1 divided by 1 by C2. Now that is the expression for effective or equivalent capacitance of two capacitors when they are connected in series. The same expression holds good for a number of capacitors connected in series, any number. So therefore in general we can write 1 upon CS is equal to 1 by C1 plus 1 by C2 plus 1 by C3 plus etc. n number of capacitors. Okay. Now one more thing is, if n number of capacitors are connected, then we will get this general expression. If n equal capacitors are connected, n capacitors of equal capacitance, then the expression becomes 1 by Cs is equal to 1 by C plus 1 by C plus 1 by C plus etc. n terms. N equal capacitors are connected in series. If that is the case, then I will get effective capacitance is equal to 1 plus 2 plus 3 etc 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 up to n number of turns. It becomes n by C, or simply I will write equivalent capacitance in case of series combination is equal to C divided by n. That you should remember. One more thing. Now this expression can also be written as 1 by Cs is equal to 1 by C1 plus 1 by C2, or 1 by Cs is equal to taking the LCM and simplifying C1 into C2. In the numerator it is C2 plus C1. Therefore the equivalent capacitance Cs, the equivalent capacitance Cs is equal to C1 C2 divided by C1 plus C2. Like that we can write. That is the effective capacitance. Now let me define the expression for effective capacitance. In case of series combination, the reciprocal of the effective capacitance is equal to sum of the reciprocal of the individual capacitances. Now we will study capacitors in parallel combination. Two capacitors are said to be in parallel if they are connected between two common terminals such that the potential drop V across each capacitor is same, and the total charge in the system is equal to sum of the charges accumulated on each capacitor. The total charge should be is equal to sum of the charges on the two capacitor. If that is the case, then the combination is called as parallel combination. Two capacitors are said to be in parallel if they are connected between two common terminals such that potential across each capacitor is the same. The total charge is equal to sum of the individual charges on each capacitor. Now look at the diagram here. We have taken two capacitor, one of capacitor of capacitance C1 and another one of capacitance C2. They are connected between two common terminals. They are connected between two. They are not connected end to end. They are connected between two common terminals across which a potential V is applied. Now here, since it is in parallel combination, the potential drop across each capacitor remains the same. ನಾವು ಎಷ್ಟಿಲ್ಲ ವೋಲ್ಟೇಜ್ ಅಪ್ಲೈ ಮಾಡ್ತಾ ಇದೀವಿ, ವಿ ವೋಲ್ಟೇಜ್ ಅನ್ನು ಅಪ್ಲೈ ಮಾಡ್ತಾ ಇದೀವಿ. ಅಷ್ಟೇ ವೋಲ್ಟೇಜ್ ಫಸ್ಟ್ ಕೆಪಾಸಿಟರ್ ಅಲ್ಲೂ ಕಾಣಿಸ್ಕೊಳ್ತದೆ, ಸೆಕೆಂಡ್ ಕೆಪಾಸಿಟರ್ ಅಲ್ಲೂ ಸಹ ಅಷ್ಟೇ ವೋಲ್ಟೇಜ್ ನಮಗೆ ಕಾಣಿಸ್ಕೊಳ್ತಾ ಇದೆ. therefore potential remains the same. ಬಟ್ ಚಾರ್ಜಸ್ ಫ್ಲೋ ಆಗಿದ್ದು ಏನಾಗ್ತಾ ಇದೆ ಅಂತ ಹೇಳಿದ್ರೆ, ದೇ ಆರ್ ಡಿಸ್ಟ್ರಿಬ್ಯೂಟೆಡ್. ಎರಡು ಕೆಪಾಸಿಟರ್ಗೂ ಇಲ್ಲಿಂದ ಟೋಟಲ್ ಚಾರ್ಜ್ ಏನ್ ಸಪ್ಲೈ ಆಗ್ತಾ ಇದೆಯೋ ಅದು ಎರಡಕ್ಕೂ ಸಹ ಡಿಸ್ಟ್ರಿಬ್ಯೂಟ್ ಆಗ್ತಾ ಉಂಟು ಚಾರ್ಜಸ್. ಸೊ ಫಸ್ಟ್ ಕೆಪಾಸಿಟರ್ ಅಲ್ಲಿ Q1 ಚಾರ್ಜ್ ಅಕ್ಯುಮುಲೇಟ್ ಆದ್ರೆ ಸೆಕೆಂಡ್ ಕೆಪಾಸಿಟರ್ ಅಲ್ಲಿ Q2 ಅಮೌಂಟ್ ಆಫ್ ಚಾರ್ಜಸ್ ಅಕ್ಯುಮುಲೇಟ್ ಆಗ್ತಾ ಇದೆ. Now since we have applied a voltage, the capacitance for the first capacitor is given by C1 is equal to, it is Q1 divided by V, because V is common. Now from this expression, what is Q1? Therefore Q1 is equal to charge on the first capacitor is equal to, it is C1 into V. Similarly, for the second capacitor, what is the capacitance is given by C2 is equal to, it is the charge on the second capacitor Q2 divided by V. From this we can write, now Q2 is equal to, charge on the second capacitor is equal to, it is C2 into V. Since it is in parallel combination, we have total charge Q is equal to, it is Q1 plus Q2. Now substituting the values, I will get, so it is C1V plus C2V. Now here V is common. If you take it outside, therefore Q is equal to V into C1 plus C2. Now cross multiplying this V, I will get Q by V is equal to C1 plus C2. Call this as equation 1. Now once again, this parallel combination is replaced by a single capacitor, which produces the same effect as produced by the combination, and hence that capacitor is called as equivalent or effective capacitor ಅಂತ ಹೇಳಿ ಅದನ್ನ ಕರಿತೀವಿ. We have to write this diagram also for the annual examination point of view. ಬರೇ ಇಷ್ಟನ್ನ ಡಯಾಗ್ರಾಮ್ ಬರೆದು ನೀವು ಈಕ್ವಲೆಂಟ್ ಡಯಾಗ್ರಾಮ್ ಬರೀಲಿಲ್ಲ ಅಂತ ಹೇಳಿದ್ರೆ ಮಾರ್ಕ್ಸ್ ಅನ್ನ ಕಟ್ ಆಗ್ತದೆ. ಅದು ನೆನಪಲ್ಲಿ ಇಟ್ಕೊಳ್ಳಿ. We have to write both the diagrams. Even series combination ಅಲ್ಲೂ ಅಷ್ಟೇ, series combination ಮತ್ತೆ ಅದರ equivalent circuit ಅನ್ನ ಬರೀಲೇಬೇಕು. Okay. Now from this equivalent diagram, the capacitance of the equivalent capacitor, we write Cp. P corresponds to parallel combination, effective capacitance in parallel combination. So Cp is equal to the same formula, the charge divided by the voltage. Now substituting this one in the equation 1, I will get now Cp is equal to C1 plus C2. So therefore, the equivalent or effective capacitance when two capacitors are connected in parallel is the sum of the individual capacitances. Now the same expression holds good for an n number of capacitors. If you assume that n capacitors of capacitance C1, C2, etc. up to Cn are connected in parallel, then what is the effective capacitance? That Cp is equal to that one. If all the n capacitors are of equivalent capacitance, are of equal capacitors C, if n capacitors of capacitance C, equal capacitance C are connected in series, parallel, then we have the expression, so Cp is equal to, I will write here, now Cp is equal to is n into C. Therefore, in the case of a parallel capacitor, in the case of a parallel combination of capacitors, the equivalent capacitance is the sum of the individual capacitances. Now, energy stored in the case of a capacitor. Capacitor is having two conductors. One is positive charge plus Q and another one is negative charge minus Q. Now here what happens? Charges are transferring from one conductor to the another conductor. Now the amount of work done in transferring the charge from one conductor to the another conductor is stored as potential energy in the capacitor. So therefore energy stored in a capacitor means it is the amount of work done in moving the charges from one conductor to the another conductor is stored as the potential energy of the capacitor. Now consider here we have a parallel plate capacitor. Now in the case of a parallel plate capacitor, we know that charge on one plate is plus Q and the charge on the another plate is minus Q. Now what is the total charge means? It is not zero. The total charge remains, it is Q. Because now this minus Q amount of charges, they are transferring from one conductor to the another conductor. That you remember. Consider a parallel plate capacitor which is initially uncharged. Now that capacitor is connected to an external power supply of voltage V, potential difference V. Then the capacitor starts charging. That means the charges are flowing from one conductor to the another conductor. Now at any arbitrary time t, let the charge on each plate is Q dash and minus Q dash. Then the potential is V dash. Therefore, by the definition, the potential V dash is given by is Q dash divided by C, where C is the capacitance of the plate. Now, I will take a small amount of charge delta Q dash that has to be moved from the second conductor to the first conductor. In order to move this amount of charges from second to the first conductor, work has to be done. Now work is done by the external potential, that is external battery or power supply. Therefore, the small amount of work done in moving this small amount of charges is delta W V dash into delta Q dash. How you write this expression? In the earlier we have studied the work done is equal to charge multiplied by the potential difference in moving the charge from one point to the another point. That we already know. Based on that relation, the small amount of work done delta W is equal to so potential V dash and the charge which we are moving, that is delta Q dash. Now, our aim is I have to transfer all the charges from the second conductor to the first conductor. So, initially the charge on each plate is 0. Now, I have to transfer in total Q amount of charges. Then, what is the total work done in transferring all the charges from the second conductor to the first conductor? Now that is obtained, therefore total work done is obtained by integrating this small amount of work done from 0 to Q. Therefore, integration of 0 to capital Q, that is delta W, that is equal to integration from 0 to capital Q. What is delta W? It is V dash delta Q dash. Now we can substitute for V dash here. I will substitute in the later into delta Q dash. Now that is equal to integral 0 to Q. What is V dash? By the definition, it is Q dash divided by C into delta Q dash. Now look here, capacitance is a constant. I will take it out. Now only left with integration of Q dash with respect to delta Q dash. We know that integral of x to the power of n with respect to dx is equal to x to the power of n plus 1 divided by n plus 1. That is the formula. By using that formula, if we integrate Q dash with respect to delta Q dash, so Q dash to the power of 2 divided by 2 with the limit from 0 to capital Q. By using that relation, I am integrating. So integral of Q dash is Q dash square divided by 2 ಆಗ್ತದೆ. Now applying the limits, I will get 1 upon C into first upper limit ಅನ್ನು apply ಮಾಡಬೇಕು. Q dash ಇದ್ದಿದ್ದು Q ಆಗ್ತಾನೆ. That is Q square divided by 2 minus lower limit, that is 0. So this is the total amount of work done in transferring the entire charges. So therefore, W is equal to, that is half Q square divided by C. Now this amount of work done is stored as potential energy of the capacitor. Therefore, potential energy of the capacitor is Q square divided by 2C. Now that is the expression for potential energy. Now this expression can be written in terms of voltage also. That is U is equal to, if I write Q square is equal to Q into Q, that is half Q into Q divided by C. What is Q by C? It is potential V. Therefore, it is equal to half Q V. It is one more expression. Okay. If you substitute for Q, now what is Q? C into V. Therefore, that is equal to half into C into V into V. So, therefore, I will get, these are the different forms for potential energy in the case of a capacitor. Therefore, U is equal to half CV square. Now these are different expressions for potential energy of a capacitor. We know that energy stored in the case of a parallel capacitor is given by Q square divided by 2C. That is the energy stored in the case of a parallel plate capacitor. Now what is Q? It is the charge. And what is C? It is the capacitance. Now we know that capacitance C for a parallel plate capacitor is given by epsilon naught A divided by D. That is the expression for capacitance in the case of a parallel plate capacitor. And charge Q, it can be written as sigma into A, that is area of cross section. Sigma is equal to Q by A, therefore Q is equal to sigma into A ಆಗ್ತದೆ. Now if I substitute these two values here, what I will get? Now look here, that is equal to Q is sigma A, therefore it is sigma A whole square into divided by 2, sigma A whole square divided by 2 into, it is C is in the denominator. Now I will substitute this value, that is epsilon naught A divided by D, it comes in the numerator. Epsilon naught A divided by D, that D comes in the numerator. Just simplifying this one, I will get is sigma square A square divided by 2 into D divided by epsilon naught into A. Now here 1A get cancels. Okay, therefore is equal to sigma square A D divided by 2 into epsilon naught. In the case of a parallel plate capacitor, the electric field between the two plates is given by E is equal to sigma by epsilon naught, or sigma is equal to E into epsilon naught. Now substituting this one, I will get E into epsilon naught whole square AD divided by 2 into epsilon naught. Now just rearrange the terms, I will get U is equal to half into epsilon naught square divided by epsilon naught, get cancels, one epsilon naught cancel ಆಗ್ತದೆ. So it is epsilon naught into E square into A into D. Now carefully look at the term A into D. A is area of cross section of each plate and D is the distance of separation. If you multiply that A into D, we will get volume of the space between the two plates. Therefore this one is equal to half epsilon naught E square into volume. Now if you take the ratio of energy stored per unit volume, energy stored per unit volume, that is equal to half into epsilon naught E square. Now this energy stored per unit volume is called as energy density and denoted by the small letter. The energy stored in the capacitor divided by unit volume is called energy density and denoted by the small letter is equal to epsilon naught into E square. Now the circuit symbol of a capacitor is like this, two parallel lines. We have this one, circuit symbol for a fixed capacitor. If the capacitor has a variable 1, then the circuit symbol becomes, variable is denoted by the arrow mark. Now this is the circuit symbol for a fixed capacitor and this is the circuit symbol for a variable capacitor. Here is one note, fringing of field lines. What is the meaning of fringing? While deriving the expression for capacitance of a parallel plate capacitor, we have worked out electric field inside the plates, that is the electric field in the space between the two parallel plates. Now this electric field is constant and it is localized, therefore it is uniform. But actually we observe at the edges these field lines becomes curved. They bend, they are not parallel, they are going to bend, and this is called as fringing of field lines. At the edges of a parallel plate capacitor, the field lines are not exactly parallel, they are going to take a curve, they are going to bend a little bit, and that is called as fringing of field lines. Van de Graaff generator. ಈಗ ಸಿಲೆಬಸ್ಸಿಗೆ ಇಲ್ಲ ಅದನ್ನು ತೆಗೆದಿದ್ದಾರೆ, ಜಸ್ಟ್ ಫಾರ್ 1 ಮಾರ್ಕಿಗೆ ಎಲ್ಲಾದರೂ ಕಾಂಪಿಟೇಟಿವ್ ಎಕ್ಸಾಮಿನೇಷನ್ ಅಲ್ಲಿ ಕೇಳಿದ್ರೆ ಬೇಕಾಗ್ತದೆ. Van de Graaff generator, it is a machine which builds up a potential or voltage, a high voltage. Van de Graaff generator is a machine which builds up a high voltage or potential of the order of million volts to accelerate the charged particles like proton, electrons, alpha particles, etc. And these charged particles, accelerating charged particles, they are used for certain experimental purposes.